Balanced binary search trees are very efficient data structures. We can insert, delete, and search large collections of data. Sets and maps are two implementations of binary search trees in C++. Without sets and maps, we would have to make our implementations if we want to use these structures. Fortunately, those things are already made for us. We will start with sets. And in order to use sets in your program, you have to put include set before or after your include IOStream. We start by typing the word set from the standard namespace. Long is the type of elements that our set will have, and now the name of our set will be A. So A will be one balanced binary search tree, but it's going to contain integers of type long, and we can think of it as a set. The method insert can be used to put elements in the set. You can notice here that number 15 is something that we are attempting to insert twice. The consequence of this is that only one of those will be in the set. Then if you type size, this program will now print 5 because there are 5 elements of the set. Deleting an element is achieved using the command erase. A.erase 57. Now 57 is gone, and now if you print the size of the set, the answer will be 4. Now we are going to add few more elements in the set, and then we will print all of them. If we add the numbers 35, 61, 72, and 100, the size becomes 8. The elements will be stored in a tree. Now we will print all of the elements in the set. For this, we will use an object called Iterator. The declaration will be left for the end. So I will first show you how to use the iterator, and then I will show you what is the line in the code that has to be written in order for the iterator to be declared. So, declaration is missing. Do not run this code in the next 3 minutes. Wait for declaration. First, we will implement. We will call the iterator I. And after we declare the iterator, we will put the command I equals a dot begin. And after this command, the iterator will behave as a pointer to the first element of the set. Now if we type our program will print 15. If we want to print the next element of the set, we should increment the iterator. Plus plus I is a command that will result in a very sophisticated behavior. The iterator will not point at 15. The iterator will find the next element of the set. So the iterator will know that the next element is the root of this small tree. So, and if we print now, star I, we will see the number 27. If we do this again, plus plus I, we will see 35. And now we are ready for that missing declaration. The way to declare the iterator is to type set. So we first have to put exactly the same command that we used to declare the set. And then 4 more dots and the word iterator I. And now you can run this program. If we want to see all elements of the set, not just the first 3, then maybe it's better to have some while loop. We first print the element I, we'll print new line, and we increment I. Iterators are complicated objects, so they are implemented already in C++, but their usage on the first sight implies that they are simple objects that we are adding. But the fact is that they have the increment operator and they have star operator. Those are not the same as increments of integers and star operators that we are applying to pointers. We can think of them in a similar way because they are analogous to pointers, but they are not exactly the same as pointers. If you try to print the iterator itself, you are not going to be allowed to do that. Iterators are also used to search for elements in the tree. We have declared x to be equal to 87, and now I equals a dot find x will either result in a success, in which case I will be the iterator to the place in the set whose content is x. If the search is not successful, I will be the iterator to the end of the set. So we will just ask if I is equal to a dot end, and if this is the case, we will print not found. Otherwise, found. The next number is, and then we can do plus plus I, and then we can print star I. So in this particular case, when x is 87, the program will say found, and the next number is 100. However, if we change this x, so it's not 87, if we put 77, and then we recompile the program and run the program again, the message this time will be not found. Maps are data structures based on binary search trees. Every element of a map has two components. The components are called key and value. The first component, key, has to be unique for every element. We cannot have two elements in the map with the same key. I'm going to give one example of a map where the keys will be the names of the countries and the values will be the populations of the countries. So we will first enable maps in our program by giving the preprocessor directive include map. That's done in the same part of our program where we include IO stream. And then in the main function, we will declare our object of type map. So we have to list. First we specify the type of the keys, and those are strings. And then we specify the type of the value, that's long. And we are going to call our map C. C stands for countries. Now we are going to put some data in our map. And this is the way how we put data. C of China is equal to, I'm going to put population in millions, so I will round it down. So it's 1,439,000,000. So I'll just put 1,439. Then I can put C of India. That's 1,300. Now, India is actually 1,380. But let me do something. Let me make a mistake. I will put 1,350. Now, if I have another command, C of India is 1,380, we will rewrite the old data. So this command becomes obsolete because we can have only one pair whose key is India. So here China is the key and the value is 1349. For the second data point, India is the key and 1380 is the value. Let's add few more countries. Behind the scene, what C++ will do is it will create a binary search tree. We can now print the size of the map. And in this situation, the printout will be 5, because at the moment we have 5 pieces of data in our map. Now we can add Brazil. We are going to use Iterator in a very similar ways as we did with set. And we will now first position the iterator to the countries C.begin. However, if we now just do the star operator, if we do star I, that is going to be a pair. The type of this will be pair, and it has two components. The components are called first and second. In this particular case, when the map has the first key of the type string, so the first component is string and the second component is long. So we can now print star I, then we must put parentheses around and then dot first. Then we can put one space character, then star I dot second. Let's put enter. Then we can do plus plus I, and we can do the same. So this first command will print Brazil with population 212, but when we do plus plus I, we will print the next element of the map, which is China and population 1439, because things will be ordered in increasing order of keys. Keys are strings, so they're sorted in alphabetical order. Deleting an element from the map is done by C dot erase, and then you can put the name US. And now it's a time for one important warning. After inserting and deleting, the iterators must be reinitialized. So I'm going to give you one example of a very dangerous code. And then you do plus plus I, that means you move to the next element. Maybe you do it again and maybe again, so you move 3 elements down the line. Now this is very dangerous line. This is very dangerous line of code because after inserting a new country, the tree may go through a rebalancing procedure. Then all the pointers, all iterators mean nothing anymore. They could be pointing to locations that are illegal. So you cannot trust any iterators. So after inserting, you must, if you want to use the iterator, you must have the line I equals C dot begin. If you're really interested in this third element, you can go there. Now we will write the program that prints all elements of the map. Instead of writing star I dot first, we can write I and then arrow first. This arrow will be replaced with star I dot first. We need to find a path between the origin and the point given by the user. the path must have the fewest number of jumps. The user will specify which jumps are allowed. For example, the user could decide that there are only 5 legal jumps. That legal jumps are by vector with components 17 and 17 or 17 and 18, or by vector 6, 7, or by vector 0, 1, or 1, 1. So our path must have only these 5 kinds of jumps. Every jump can appear multiple times, but the total number of jumps has to be as small as possible. The user may decide that the destination is the point 1823. We are now going to build one path between the origin and the point 1823. And this first path will not be the one with the fewest jumps. This one is just to show an example how a path is made. The first jump in the path will be 17, 18. 17 steps in the x direction and 18 steps in the y direction. Our second jump will be by this vector. 1 step in the x direction and 1 step in the y direction. And then our next jumps must be by this vector. So the first, here the total number of jumps is 1 by this big vector. Second jump was 1, 1, and then we had 4 jumps by vector 0, 1. So the total number of jumps on this path is 6. There is a path with fewer jumps. There is a path with only 5 jumps. We will first make 3 jumps of this kind. Each jump will be 6 steps in the x direction and 7 steps in the y direction. With these 3 jumps, we have arrived to the point with coordinates 18 and 21. We need additional 2 jumps in the direction 0, 1. So the total number of jumps is 5. The user input consists of a positive integer m followed by legal jumps, m jumps. After these m jumps, the user provides the destination point. The point will have 2 coordinates, x and y. Our program must output the number of jumps in the shortest path and the sequence of jumps that have to be made. So in this particular example, the sequence of jumps should be, or this is also acceptable output, or any output that would take us from 0, 0 to 1823. We will first construct a recursion that solves this problem. Then we will use binary search trees to improve the recursion. recursion will have exponential complexity. And by using binary search tree, we will reduce the complexity of this particular problem to polynomial complexity. Fewest jumps will be the name of our function. It receives allowed jumps, which is a sequence of pairs of points that are allowed to be used as our jumps. It will also receive the number m, that is the length of this sequence, and the recursion will also receive the target point. Then the function will behave like it's a big boss, and the function will hire employees to perform easier tasks. So the function will go over the sequence, take every possible legal jump, and subtract that jump from the target point. So in this particular case, if these 5 vectors were the allowed jumps, then we are going to first take the vector 0, 1, subtract from the target point, and obtain new target. And then we will hire an employee. Employee will find the path with fewest jumps from the origin to this point. The employee will then tell us how long is this path. After this employee has finished the job, then we will subtract the next vector from the target. We get a new point. We hire a new employee who will tell us how many jumps the shortest path contains from the origin to this new point. And then we record that number. We put it somewhere on a piece of paper. Once we subtract 6, 7 from the target point, we get a new point, and we will hire an employee who will tell us what is the shortest path from the origin to this new target and the number of steps that this shortest path will have. And we continue in this way. So we then hire another employee for the situation where 17, 17 is subtracted from the target point. This recursive function will have exponential complexity. The big boss will hire 5 employees, but each of those 5 employees will hire 5 another employees, and each of them will hire 5 more. So in the end, if our point is very far away from the origin, it could easily reach to 5 to the 100, and that's not possible for our computer to handle. A lot of employees will be asked to find the shortest path from the origin to the point 1, 1. And we are going to save that work. So we are going to do this work only once and store the result in a map. So we are going to avoid the repetition. Recursions are not going to perform the same job twice. Map will be used to store the result. Our map will be called knowledge. This knowledge will be passed by reference, and it will be one of the arguments of our function. So the employees, when they are hired, they will take this big map, and whenever they perform some job, when they discover one of the shortest paths, they will put that to this knowledge, and this knowledge will grow. The keys of the map will be points, and they are targets of our paths. The values will be the length of the best path, and by best we mean a path with fewest jumps. However, since in our problem we have to also reconstruct the best path, not just to return the number of jumps in the best path, our value has to contain one more information. If we only have the length of the best path as a value in our map, we would not be able to reconstruct the path. We would be able only to tell what is the length of the shortest path. But our value is going to, in addition to this length, it will contain the last, and we will call it victory jump or winning jump. And now we will start making the program. We have to create a class that will hold the x and y coordinates of our points. So the class will be called point 2D. And its public members will be the x and y coordinates, and we need the comparison operator. Since we will be adding and subtracting vectors, it's going to be very convenient to add the operators for addition. Operator once we have this kind of operator, the following command is going to be legal. So we can have point 2D A, then we can have point 2D B. We can set coordinate of x, coordinate x of A to be 7, y coordinates to be 20, x coordinate of B to be 10, and y coordinate of B to be 25. Then the command A plus equals B would change A. A is now changed from 720 to 1745. The comparison operator is necessary because maps in C++ are organized as binary search trees. Binary search trees can work only if there is a way to compare the values. This is not going to be something that we usually do in geometry. So we have learned that complex numbers and points in two-dimensional space do not have a natural way of comparing which point is smaller than the next one. So we don't have those. But here we are just going to make sure that every 2 points are comparable, and we are first going to compare x coordinates, and if one point has a smaller x coordinate than the other, that point will be pronounced as a smaller point. If they have equal x coordinates, then y coordinate will be the tiebreaker. So we will first ask if x is smaller than b dot x, then we return 1. If x is bigger than b dot x, then we return 0. If our program has survived both if statements, that means that x coordinates are the same and we need a tiebreaker. If y is less than b dot y, we return 1. Otherwise, we return 0. Otherwise means either b is bigger than our point or they're the same. The function fewest jumps has to return the length of the path with fewest jumps and the last point on that path. We are going to create a class that contains the two components. One component is the length of the best path and the other component is the last point. That class will be called fj info. It stands for fewest jumps information. That's what our function will be returning. It will return the length, shortest path length, which is the number of jumps on the shortest path, and point to the last jump. We are also going to create the constructor that sets these numbers to zeros. Our recursion will return fj info fewest jumps. The input is the map with all the knowledge. So map has keys that are points. fj info are values, and the map will be passed by reference. And then we will need the sequence of all legal jumps. We will need the length of the sequence, and we will need the target point. We will declare one object of type fj info, and that's going to be the winning jump. We will call it w jump, and it stands from winning jump or victory jump. If the target has both x and y coordinates equal to 0, our recursion is successful and it should return this object w jump. Now we can have situations where the path doesn't exist. So we are going to notice those paths if one of the coordinates becomes negative. And in that situation, we really want to transmit information that the search was unsuccessful, and we will do that by modifying the length to -1, and this is going to be the symbol, that the sign that the search was unsuccessful. If target x coordinate is less than 0 or y coordinate is less than 0, we will now return w jump. This modified w jump whose length is -1. We declare an iterator that we will use to search for this point target in our map. iSearch is a knowledge find target. We'll now take this to a new page. If iSearch is not knowledge and this means that we don't have to call the recursion. We already know the answer. We can immediately return iSearch second. The type of this variable will be fj info, and that's precisely the thing that we need to return. The counter that will start at 0 and run until m, so we can go over all possible jumps. We will declare a variable target for our employee, we will also declare a variable where employee is going to store the result, fj info, winning jump from employee, and we will have a while loop. While I is less than m, so we will start target for employee. We'll start from our point, and then we will subtract. So now if the point has both coordinates positive or 0, we have to do some work, otherwise we don't do any work. Our jump is impossible, so we will just increment I. But if the jump is acceptable, then we will first check whether we need to call the employee. If we found something, and we test whether we found by comparing this iterator with knowledge and W, the winning jump from the employee is I search second. Is we now make recursive call. Fewest jumps knowledge or allowed jumps M and target for employee. We now need to test whether there was a path that employee has found, because it could be the case that there is no path from the origin to a point that we gave to our employee. We will test whether SP length is bigger than -1. And if it is, then we have to test whether this path is better than what we have so far. So we first check whether we have some path. So if we have no path, then this path we just found is the best. Or this path is longer. We are adding 1 because we made the last jump. So if this is the case, our path has to be improved. After the while loop, the object wJump contains the length of the best path and the last jump of that best path. Now we will update the knowledge and we return wJump. We will not implement the main function here. Please go to the course website and you will find the complete code.